Greetings, mathophiles, and welcome to a discussion of what are known as separable differential equations. We'll see momentarily what it means to separate a differential equation, but if you're able to take this approach with the differential equation, it's actually a nice thing because it's a very straightforward route to a solution, provided that you're able to perform a couple of integrations that are going to arise. We have in front of us a very famous differential equation, dy dx equals ky, in which the rate of change of some quantity y is directly proportional to the magnitude of y. And we have additionally an initial condition that y of 0 equals 5. The way you go about separating a differential equation is to haul everything that has anything to do with one variable to one side, and everything that has anything to do with the other variable to the other side. And if the structure of the equation is such that that can be done, the equation is said to be separable. And so I can, for example, divide by y and multiply by dx. And I will have succeeded in separating in that there are no x's on the left, there are no y's on the right. Now, this may be doing violence to some things that you were told about the dy dx notation. Probably somebody told you at some point that it was a piece of notation that represented a derivative. It was not a fraction, couldn't treat it like a fraction. Well, we're going to sort of treat it like a fraction here. And the short answer to the question, how can we do that, is that it works. There is a longer answer. This is a legitimate technique, so you don't need to sweat that we're doing something shady or that we're somehow going to get wrong answers if we take this approach. It's perfectly useful. It's just maybe a little bit unexpected for some of you to use the notation in this fashion. What we're now going to do is integrate both sides. We know if two functions have equal derivatives, they differ by a constant. And so the integral of dy over y and the integral of k dx ought to also differ by a constant. So if I integrate 1 over y dy, I get natural log absolute y. If I integrate some constant dx, I just get that constant times x. And then we need a constant of integration somewhere. And my preference is to put it on the independent variable side. Now, you may say, why don't we have two? Why don't we have one on the left and one on the right? Because after all, we did two integrations. Yes, we did, but we could always subtract one of those constants from the other side, rename it as a new constant, and be perfectly fine. So it's plenty good enough just to have the one. Now it's time to think about our initial condition. So y of 0 was 5, which means the natural log of absolute 5, also known as 5, is k times 0 plus the constant, which means the constant is the natural log of 5. So we have natural log absolute y, and I'm going to lose the absolute values. And the reason I'm going to do that is that we have an initial condition with a positive y. The natural log of absolute y is discontinuous at 0. So if we have a positive y in our initial condition, that's not going to give us any information about what's going on with negative y's and vice versa because of the discontinuity that lies between them. So if we have a positive y in the initial condition, we just are limiting ourselves already to y's that are positive. And if we're being careful, we're probably going to say this. We're not always as careful as we should be. So anyway, the natural log of y is equal to k times x plus c, but c was the natural log of 5. So y is e to the kx plus ln 5, but that is e to the kx times e to the ln 5, but e to the ln 5 is 5. And this is an incredibly familiar result. This is an exponential growth or decay function, depending on what k is. So there it is. Now, what if our initial condition had been such that y was negative? What if it had been y of 0 equals negative 5? Well, In figuring out the c, we would have taken the absolute value of -5, which is 5, and c would still have been ln 5. The moment where it would have mattered is up here, because we would be talking about then negative y's. You can't take the natural log of a negative number. So what this would have been, I'll write it down here, is natural log of opposite y equals kx plus ln 5. And it would have worked out such that we would have had the opposite of y is equal to 5e to the kx, or y equal to -5e to the kx. And that would then have given us the -5 that we need when we plug in a 0 for x. Here is a second example, and to the best of my knowledge, this example is not famous, but it does give us another look at this process, and it has certain features that are, I think, good to see in an example, and you'll know what I mean by that when we reach those points. So, dy dx minus xe to the y is equal to 3e to the y. And I think the first thing that I want to do is to combine and factor, so I get that e to the y present only once, so to speak. So I'm going to add xe to the y to both sides, and just to save a little room on the screen, I'm also going to factor out the resulting x plus 3. So this is going to be x plus 3 quantity times e to the y. And now we are in a position to separate. We can divide both sides by e to the y. We can multiply both sides by dx, and so we have dy over e to the y equal to x plus 3 dx. Now, time to integrate. And you may look at that integral on the left and say, well, I integrate 1 over something, I get the natural log of the something, so it's 1 over e to the y, which is y. And of course, a little reflection should cause you to appreciate that that doesn't make sense if you roll it in reverse. I think the pro way to approach this one is to rewrite it as e to the op y dy. That gives you some pretty strong guidance on how to integrate this thing. The integral on the left is just e to the op y with an extra -1 for the chain rule. So we have op e to the op y equal to x squared over 2 plus 3x plus a constant of integration. This is usually the best time to plug in and figure out your c, because you tend to have things in a sort of more opened up, if you will, format. So if I plug in 0 for x and for y, e to the 0 is 1, with a negative sign out in front is -1. We've got 0 plus 0 plus c, and so c is -1. And so I guess I'll rewrite this up at the top. So we have op e to the op y equal to x squared over 2 plus 3x minus 1. We need to solve for y. First thing we'll do is take care of that negative sign out in front. So e to the op y is negative x squared over 2 minus 3x plus 1. Then we got to take care of the exponentiation. So op y equals natural log of this stuff. And finally multiply through by -1. And there we have it. Now, there are things we can do with this, right? The opposite of the log of something is a log of the reciprocal of the something. That probably doesn't simplify anything for us, so I'm not going to be rewriting it in that fashion. We also need to think about domain, because this function is only going to be good when the argument of the natural log is positive. And you may find yourself in situations where you're asked to go on and take that final step and say, all right, what is the domain? What are the values of x for which this is the solution to the original initial value problem? Because it's not going to be for all x's in all likelihood. Hope this quick explanation, a couple of examples, have been helpful to you in getting a start with separable differential equations. Happy mathing.